Okay, so this week we're going to do static and kinetic frictions. So you log on to Canvas, click on modules and scroll down to find lab menu activity. Click on lab 7 and this is, I'm going to bring up the file. So it would look like, so this is the file. Okay, so lab 7, is about finding the coefficients of static and kinetic frictions of an object. So you're given an object that comes with two different surfaces. One is made of wood and one is made of felt pad, and you want to find the static coefficient and also the kinetic, the coefficient of static friction and also coefficient of kinetic friction. All right, so the experimental setup is like this. So you have the force sensor, which is used to measure the tension in the string. And this is what we call the friction block that comes with two different surfaces. So let's say you have one surface that either it is wood or felt pad. Let's say a wood surface in contact with the dynamics track. And you have the force sensor, and you're going to tie the string to the hook of the force sensor, and have the thread wrap around the rotor motion sensor. On end, there's a mass and the mass holder. And to ensure that you have good data to work with, you want to make sure that the track is leveled. You also want to make sure that the string is parallel to the tabletop. And then we're going to follow the same procedure whenever you are dealing with a force sensor. That is, you need to zero the sensor before you take the measurement. So how do we zero the sensor? You would have one hand. You will have one hand holding the string, and then so that the string does not exert any forces on the hook. And then have another hand to press the tail button to zero the sensor. You only need to do it once for each scenario. So that's it. When you start doing the wood, then for the kinetic, then you zero sensor. When you use the wood for the static, you zero the sensor. Okay. So once you have the cell like this, we need to understand how this works. So this is when you're dealing with the friction. Okay, so contrary to what you have in previous labs, you're dealing with approximately frictionless, motion. But in this this is what we call a friction block. It does have a friction, so friction has to be taken into account. So how to calculate the maximum static, the coefficient of the static friction? So if you remember, if we draw a free body diagram, okay, how many forces are acting on this? If the whole thing, so let's say if you place some mass on this, the whole thing is not moving, meaning that there must be some sort of friction acting to against the motion. Okay, so this. The combined mass, we use capital M to indicate the combined mass, which is the mass of the force sensor plus the mass of the friction block. And then you have the outward normal force. These two forces have to be balanced to each other. Okay, N is equal to mg, capital Mg, because this thing is not moving vertically. And this thing is not moving horizontally either, meaning that you already put some mass on the mass holder, meaning that there's a friction. There's a tension in the string, right? So we're going to say T, and that T, and then it is not moving, meaning that there must be an equal amount of force, but in the opposite direction that's opposing the motion. So this is your static friction. So based on this, if this is still not moving, then the tension is always balanced, the frictional force. So your frictional force is not a constant value. Your frictional force is going to change because depending on what tension value it is in the stream. Okay. However, when you continue adding the masses on the mass holder, the tension is going to increase. So when the tension increases in such a way that it is big enough to overcome the static friction, then we have reached the critical point, and that value, that tension is going to be balanced by the maximum static friction. Okay, so in other words, when the object is about to move is when tension is greater, is equal to the maximum static friction. I should say. So T, when T is equal to the maximum static friction, this is when the whole thing will start to move. And so experimentally, you will continue to add the mass until you see that the whole thing starts to wiggle, meaning that it's just about to move. Then you have found the maximum static friction. Okay, and the maximum static friction, if you remember, can be calculated using this equation, the mu s, which is coefficient of static friction, and then times the normal force. So from here, we can see that your mu s can be calculated by setting that T over N, and your N is equal to capital MG. Okay, so this expression we're going to use. We're going to treat that as an experimental value of the maximum of the coefficient of static friction. Okay, so T, tension over the mg, so tension will be given, and capital M, the individual masses will be given, so you need to find the capital M. And G, of course, is positive 9.8. So when you do that, you get the experimental value of the coefficient of static friction. Now, what about theoretically? Theoretically, let's say you when you do the experiment, when you add in masses on here, this whole thing here, it's going to produce the tension. So the tension here is equal to, let's say, the mass, the maximum value that you got. Let's say we use the M here. The M here, when you keep adding the M, that when it reaches the point that the whole thing starts to wiggle, that mass, we call that maximum M, and that is equal to G, right? You have the maximum M here times G, that gives you the tension, and that must be the tension must be balanced by the tension must be balanced by the mu s and here. So you have the mu s times N, and your M is capital Mg. So the G here cancel, so your mu S theoretical is equal to M max, and then over the capital M. Okay, so you can see that both actually are from the experiment, but we're going to treat, but in order to do comparison, one of them we're going to treat as an experimental value. So we use this expression to treat that as experimental value. And then we're going to use this expression to treat that as a theoretical value, okay? So then you can do comparison. All right, so the max, the M max is where, the amount of mass that you put on this until you reach a point that this whole thing starts to wiggle. And this is what we call the maximum mass. Okay, all right. So this maximum mass value will be given, and that already includes the mass of the mass holder. Okay, so whatever M max you're given, use that value in the equation. You'll be able to calculate the mu s. Okay, so that's how. And then once you're done with the one service, you flip it. Do exactly the same thing to find these two quantities for another service. Okay, so this is when the whole thing is now moving. So this object, this system is subject to the static friction. In order to find the mu s, you want to create a scenario that it reaches the maximum static friction, so that you can calculate the mu s. Now regarding the kinetic friction. So for kinetic friction is that, the whole thing is already moving. So to do that, so let's draw a free body diagram again, okay? So this is your capital M, G, and it's going to be balanced by normal force because the whole thing is now moving in the vertical direction. Now, horizontally, we're going to add enough mass on this mass holder so that the whole thing will actually create a motion. meaning that this thing is subject to kinetic friction. So we know that there's the frictional force, and this is the kinetic frictional force, Fk. Okay, so just based on this, we know that you can set up equations. So you apply Newton's second law, tension minus Fk, right? So this is the horizontal net force that must be equal to the M here, capital M, and then times A. And then we also know that your Fk can be calculated using mu K times the normal force. And your normal force in this case is capital Mg. So we're going to replace Fk with this expression. So we have the tension minus mu K times capital M times G, that is equal to Ma. And our goal is to find mu K. So move this to the right side and move this to the left side. So altogether, you'll get your mu K, that is equal to tension minus capital Ma, and then over capital M, and then G. Okay, so we're going to treat this as your experimental value. Okay, so tension will be given. The M is the mass of this two thing, and your A, you'll be given data to calculate A. You use the average value of the acceleration in this equation, and then you have the M, which is the same M here, and you have the G, which is 9.8. So you can calculate this experimental value. So make sure that when you do calculations, everything has to be in SI units. If you're not in the SI unit, you're going to get a huge error because you're just using the wrong units. So what about theoretical mu K? So for theoretical mu K, we're going to keep this. This equation. This equation comes from this diagram. When this is in consideration. Now let's look at, we're going to use, because this is actually a two-body system. When I say two-body, we have one body here, and we have the one body here. Okay, if you look at expand the system to include this two-body, so in this two-body system, you can draw another free-body diagram. So the dot here indicate the mass, this whole mass here. So there's a tension, and then there's a loading mass. So I'm just going to use a lowercase m, and then the G, right? They are not equal to each other. Remember, this whole thing is moving. So it's not static. So T is not equal to mg. Instead, because the whole thing, if this is moving leftward, this whole thing is moving downward, it means that your mg is going to be greater than tension. So you can set out another equation, which is your mg minus tension is equal to ma. So this is a very similar to the two-body system that that we discussed in the lecture, and also the problem solving. There are several problems that deal with a two-body system, and so you would draw two free-body diagram, one for this one and one for that one. This whole thing, so you set up one equation. This based on this free-body diagram, you have this equation, and then based on this free-body diagram, you have this equation. So if you look at this, you have two unknown, tension is not known, acceleration is not known. What we can do is that we can add these two equations together. So when you add these two equations together, tension get canceled. So on this side, so I'm going to write it here. So on the left-hand side, you have the little mg, and then minus mu k times capital Mg. The symbol are very important. You don't want to get mixed up. And then that's equal to, on the right-hand side, you have the capital M, you have little m, so you have the little m plus capital M, and then times the acceleration. Now our goal is to find mu k. So move this term to the left-hand side, move this term to the right-hand side. So you have the little mg minus little m plus capital M times the acceleration, and we're going to divide the capital mg, and then you get your mu k. Okay. So we're going to treat this mu k value as the theoretical. So again, this is rather arbitrary, but because both theoretical expression and the experimental expression, they all involve direct measure of quantities. So you have to decide. So we're going to pick this one as a theoretical and this one as experimental, and we're going to compare their values. Okay. So again, when you do this, everything has to be in SI unit. This is the little m, this is capital N. They are different. They have different contexts. They have different values. So make sure that you don't use the wrong numbers. Okay. And A, of course, is from the the A here is the same A here that you'll be given the values to find the average value. Okay. So that's basically what you're going to do. And experimentally, so let me see. So the data will look like this. And so if you read through the steps, you will say that you have to record the tension when the whole thing is not moving for the kinetic friction. And that's because once it moves, it experiences a frictional force. So whatever tension you measure will not be accurate. So you want to measure the tension in the string before it moves, and then release the block, and then the whole thing is going to be moving. So when it's moving, tension value is going to be modified because due to the net force in the string, will be modified because there's a frictional force acting on the system, right? And the equation that I just went over, they can be found in here. So make sure that again everything has to be in SI unit, and how much mass that for the kinetic friction. How much mass do we add to the holder? So if you read through that, we'll put 150 grams. So it's 150 grams. 150 grams is the mass that we add, but then you have to also include the mass holder, the mass of the mass holder. So you want to use 150 grams plus 3.5. This is your M, right? Okay, so your M, the little m is not 150. Your little m is 150 plus 3.5. Okay, all right. So let's look at the table. So the table looks like this. So as I mentioned, you were given the mass of the blob, mass of the sensor, and all that stuff. So I think this will be a good time to actually, share the data file with you. So the data, let me see, is this the data? Yeah, data. So the data you're given is this. Okay, so you have the mass of the block, the mass of the sensor. You need to add them together to give you the capital M. And then remember to convert that to kilogram. And so the capital N is the same capital M here, okay? And regardless which surface that's in contact with the dynamics track, the M does not change. So the M goes into these two spots. And for the static friction, the tension value are given. The maximum mass that when it starts to wiggle are also given. And the mu s and mu s theoretical and experimental use the equation in the in this lab activity to find the value, and you'll get the percent error. And then for kinetic, tension value is given. Acceleration, you need to find the average acceleration, and that will go into this spot, and then use the equation that we just went over to calculate experimental and theoretical value of mu k, and then find the percent error. Okay, so in this activity, you're given two data files. One is this one, and the other one is Excel file. Let me see, where is my Excel file here? Okay, so these are the value for the acceleration. So you need to find the average. You don't have to find the standard deviation. You just need or standard error. If you want to find the standard error, in fact, why don't you find the standard error as well? Okay, so find the average and find the standard error. Just to see how the data are close to the average value, or the data are actually all over the place. Standard error can give you that give you an idea how far how good how how the data compared to the average value. All right, so this is for the file service, and this is for this column is for the width. So find the average, find the standard error, and then enter that information, enter that into in here. So you have the acceleration, and then your A will be able, you can calculate your A, use and then just find the mu K value. Okay, so that's basically what you want to do. Remember the m, the little m in the equation. Let me just go back to the this one. So the little m in this equations, not in here, but in the little m here in equation 6, that m is 150 plus 3.5. Okay, so so that's basically what you want to do for this this week's experiments.